Okay, so chapter, I think it's chapter 6 in your book, it's chapter 6 here as well, um, is all about light and electrons and light emission spectra and all of those kind of things. The two guys that were really influential in all this area of study, these guys are the major contributors. Bless you. Einstein and Planck, and we'll talk about what each one of them did. Um, when we think about quantum theory, you guys remember from Chem 1, like the 1s2, 2s2, 2p6, 3s2. So all of that ties into like where the electrons are, and we're going to get to all of that. But quantum theory also led to some really like modern things and some modern discoveries. So we're going to say that it led to many, I'm just going to say tech developments. So we're going to look at it in the atomic way, but it's important to know like the influence it had in modern times. So it led to the development of things like LED lights, and LED lasers. I'm trying to think what else. Computer parts, or the way that computers work, setting up new ways for them to work, cell phones. So there's just a whole bunch of different things that influenced fiber optics and the way all of that stuff works. So that's great. There's chemistry involved in some of that. There's a lot of physics involved in that. But we want to know, like, how is it important to us and what we're studying in chemistry right now. So first I would start by saying basically that it just helped us understand light. We'll say its nature, and the way it works. It wasn't until really like the 1900s that we had this idea, like, because we would heat things and we would see the color change if we heated it long enough, but we didn't really understand the link between the intensity of light and the emission of the intensity of heat and the emission light that was given off. So all of this sort of helped change our description. And our thoughts about light. So it was big influence. Basically, we can say it gave us tools. Tools for understanding. Anybody remember what that was called? Way back from Chem 1? What kind of model it was called? Good old Max Planck came up with the beginning of it. You sound very smart when you say you're studying it. It was called quantum mechanics, or the quantum mechanical model. And even though we touch on it in chemistry, we're concerned with it in terms of electrons and how the electrons work to give off their energy or to gain energy. Really, quantum mechanics was a new area of physics. That's where it started. That sort of overlapped to chemistry. Because it helps correctly, let's see, describe atoms and electrons. Now, mind you, at this point, when Planck started working on this, we'd already figured out like where the electrons were. We had our electron cloud theory sort of developed, but we still didn't have a great understanding of simple things like, well, they seem simple to us now, like why, if I hold a fork in a fire, does it eventually begin to glow? Or how many of you have seen one of those kitchen stoves that has like the glass or the black glass top, and you turn it on, and if it's on long enough, eventually it glows to yellow? We didn't really understand how all of those things worked. We just knew that they worked. So it wasn't until these guys started working that we started making sense of some of those like really common everyday things that we see all the time. So we can start to use these quantum mechanics or the quantum mechanical theory to do some things. Number one, we can say it's used to describe the arrangement of electrons in atoms, which we call electronic structure of the atom. And it helped us figure out things like the number of electrons present, more specifically than what we could do before. It helped us understand, I'm going to say, the distribution of electrons. What do I mean when I say that? The distribution of electrons. What am I really saying in a nice short way?
Where electrons are on that.
Yeah, where, or at least a prediction of where. Pretty darn good prediction, actually. But you got to remember Heisenberg's uncertainty principle, which we'll get to later. And it also allowed us, and this is probably the biggest thing, to find the energies of various electrons. The energies while they're within the atom, and the energy required to remove them from the atom. That's important because it tells us kind of what we can do with those atoms in certain devices. Well, that's great, but how did it help us further in chemistry? And this is a big one. It really helped us understand the modern periodic table. How could that be? Or what did it help us understand? What does all this have to do with? What? Could have to do with the ions, but more specifically, what's it all have to do with within the atom? The electrons. And what do electrons give us, or what do we need to make them move? Good, energy. So it helped us understand the modern periodic table, and because we can start to understand the energy of electrons and how they move around, we can start to understand light, but we can also start to understand the periodicity of the periodic table. Ooh, what does that mean? Periodicity.
How periods interact with each other, or like how they're similar to each other.
Oh, good, good. That's the word I wanted. Periodicity means like why I'm just going to say rows or groups, families, what else? Blocks, which we'll talk about in this unit, have the same trends. Like, you all should know this at this point. If you look at your periodic table, what's group 1 called? Alkaline metals. And what's true about everything in that group? Yeah, they all react similarly. They react more vigorously as I move down. Why would that be? What do they have more of as I move down the row? Electrons. So it helped us start to put all those pieces together. And we'll continue to put them together over the next couple of units. Okay. So first we'll talk about the wave nature of light, which you should have heard of before. There should be some overlap here with what we learned basically about water waves a little bit last year. So when we think about electrons in the electron cloud within an atom, what we understand about it I'm going to say about atomic structure. Comes from, number 1, light analysis, or we could say emission, and absorption for the elements. So it's all about emission and absorption when we start to think about this. Remember in Chem 1 you probably did flame tests, which we will do again. We had to supply some energy. We got the electrons to jump around. You get a specific color. That color fits on a spectrum. It tells you about the energy of the light that's emitted. What's the light we see called?
Visible light.
Yep. So visible light. And we can say that visible light, I'm going to say, is a small part. It's pretty small. Part of the electromagnetic spectrum. Yes.
So if you're colorblind, does that mean that your eyes just like aren't able to tell the difference between waves? Because like the red-green colorblind is the most common. And those are
Yes,
the two
yes.
waves that are closest.
There's a definite correlation between being able to pick up the frequency of light and for your brain and your eye to be able to connect with each other with that particular. But there are also some underlying genetic factors that play into that too. But yeah, that's a good observation actually. So let me ask you this. What is this type of energy called, this light energy? What's the real name for it? Do you know that?
It's radiation.
It is radiation. What kind of radiation?
Visible light? Or,
Yeah, visible light is part of that spectrum.
well, I'm question.
I was just seeing if you remember. You may not.
I know UV, gamma.
Yeah, that's the spectrum. It's simply called the electromagnetic radiation. So when we have the electromagnetic spectrum, it's part of it is electromagnetic radiation. And it carries, basically this is carrying, or carries, I'm going to say carries energy through space. And that energy, what kind of energy is that? I think you already said it, Kyle.
Radiation.
Radiant is what we call it. Radiant energy. So when we're talking about all of these things, within the visible spectrum, we're talking about radiant energy. Now, check yourself here. Can you remember the visible spectrum? What is it? You should know, Bridget. Roy G. Biv, Mr. Roy G. Biv. What grade did you learn that in? Yeah, it's forever ago. Now, I think at the very back, we'll look at this right now, somewhere, you should have a picture, oh, I don't know where it is, of the electromagnetic spectrum. I don't know, I should have one in here somewhere. I thought I saved myself one. Did y'all find it? There it is. Okay, so let's look at this. So look at that center, that part in the middle, the part that we see and we seem to be most fascinated with. Visible light, it's a pretty tiny part of that whole spectrum. When I start down here with gamma rays, what's true about my wavelength?
Very small.
It's very small in meters. Very high frequency. So I'm going to call this low. Remember the symbol for wavelength?
Is it a lambda?
It is lambda. Low wavelength, which is lambda. And I'm going to call this high frequency. Anybody know what that is? I know it looks like a V for velocity, but what's that Greek letter?
No, it's rho.
It is nu.
Use like the U.
Yeah, it doesn't always have that above it though. It's kind of like a mu is like mu's like that. Nu is like that. And sometimes I don't know, it depends on the computer. Sometimes the mu looks like that. It's like a U. For me, the mu is a U, the nu is a V. That's just a, so anyhow, down here I have exactly the opposite. And I'm going to say, instead of low, I'm going to say small. I think that makes it more clear in your brain when you picture it. If I come down here, I'm going to say long wavelength. And I'm going to say low frequency. So if I'm looking down here and I'm looking at this 10 to the third, which is basically a wavelength that's about how long? What's 10 to the third in metric system? About 1,000 meters, yeah? So this is kind of like football length, football field length. Oh my gosh. If I come down here and I look at this 10 to the negative 11, that's about the size of a diameter, yeah, of a nuclei. So there's a huge difference between the two. When I look at the visible spectrum, obviously down here in my purple area, I have the highest frequency. In my red area, longest wavelength, lowest frequency. We'll talk about what frequency and those things are just in case we need to refresh on that. So be sure you can use this visible spectrum in terms of wavelength and frequency. Okay. So when we think about electromagnetic radiation, oh, I know, there was one other thing I wanted to show you. Where's that? You have this too. Back here. You're going to get these problems and you're going to have all different types of units, all part of the metric system. We've done this before. be sure you can make those conversions. Like if I have something, let's say it's in nanometers. Let's see, I have 589 meters or something like that, and I want it to be nanometers. I just add that 10 to the negative ninth on there, and that makes that nanometers, right? Remember our conversions from way long time ago? So pay attention to your units. That's basically the point of that. All right, so we've got quite a few things here when we think about all electromagnetic radiation. First of all, if I move it through a vacuum, all electromagnetic radiation moves through a vacuum at the same speed. It all moves at that speed. Now, lots of times, you'll see that as 3.0 times 10 to the 8th meters per second. What is that? Speed of light, good. What's the symbol for the speed of light? C, and this is a constant. We should also remember that electromagnetic radiation, the waves, have properties like water waves, like all of those ones we went through at the very, very end of the year in physics online. So electromagnetic radiation moves in waves that are similar to the way that water waves move. They have the same traits, the same tendencies, which means these waves are periodic. And when I say periodic, anytime we say periodic, that means repeating patterns, which really can apply to periodicity as well. So I've got, in this case, I've got repeating patterns of highs and lows. Now, see if you can remember this. What do I call the highs? Crests, or sometimes you'll see the word peak. Oh no, I'm not talking to you. Crests or peaks. Different books call them different things. And I call the lows, only one word usually shows up, trough. When I talk about electromagnetic radiation, just like when I talk about water or many other forms, I'm really talking about this wavelength. What can you tell me about wavelength? Could you define it for me? Crest to crest or trough to trough. So this is the distance, I'm going to say between two adjacent crests or two adjacent troughs.
Could you say the distance of one period?
Could you say what?
The distance of one period.
You could also say one wave cycle. So all those things are kind of interchangeable, but you have to understand what period means. So, what?
Could you do like it doesn't necessarily have to be a crest or trough, just that it's like.
Well, if I'm saying one wavelength, by definition, it's crest to crest, trough to trough. You always pick a high or a low to start with. Could you technically start in the middle here and find the middle over here? You could, but that would be not a good way to do it.
Okay.
So when you see a drawing of this, you should see, whoops, like a series of waves, and you would be, could be marked here to here, and it could be labeled 1 lambda, or you could be marked here to here, whoops, I went too far, and have 1 lambda. It just depends. But those are the two traditional ways to see it. Now what's the other word that goes with this? Frequency. So let's talk about that just a little bit. Define frequency for me. Annie, can you do it?
How often,
Can you help her, Bridget? I'm trying to think of my people I had last. I had, oh, but Katie had this last year.
it's like how small the wavelengths.
Okay, that goes with it. You're right, absolutely right. Because if they're closer together, what are they? More or less frequent? More frequent. Riley, can you help?
It's how many times a wave passes through a certain point in a certain amount of time.
Okay, so let's simplify that a little bit more. I'm just going to say the number of complete, and you can either see it this way, wavelengths, or sometimes you'll see cycles, because a cycle is 1 wavelength, but pass a set point. And what's the magic time? 1 second. Yes. And the last really important thing to remember is that all traits of this electromagnetic radiation are due to, I'm going to say, the periodic oscillations and intensities of what two things are involved here, of the electromagnetic field not a room with the light, or with I could say it a little better if I said with the radiation. And we'll talk more about that later. But you just need to understand that all of these traits are due to both electric and magnet and how they interact within our atmosphere and within the atoms. It gives all light those periodic tendencies, or those wave-like tendencies. Okay. I think we're going to get through all this. All right, so we're going to do a little bit of this working with wavelength. And I don't. Oh, so some of this you already know. Like Bridget already said something about it. We looked at it in physics. Pretty common sense. You should be able to look at two different waves without any labeling and talk about their frequency, talk about their wavelength, talk about which one is moving at a higher velocity if we want to talk about that. Can you look at those two waves and figure those things out fairly easily? Yeah, you should really be able to. Even without me talking for 25 minutes about it, you should be able to do that. Up here at the top, I didn't leave a space for this, I just thought of it. But I do want to make sure that we put something down about how different types of electromagnetic radiation have different properties due to wavelength. Okay, we're going to stop for a second.